hello everybody. Thank you to be here again to attend. Just waiting for those two residents here that are a little bit disturbed, obviously. So welcome to this new conference, which is the inaugural talk of our research resident Giuseppe Orlando, who is here already for some time, I think a few months already.
From December.
Yeah, from December, exactly, from 2 months. And it is the first inaugural conference of an economist. We already had an economist, but we hadn't had yet this idea of an inaugural conference. And Giuseppe told me that at first he proposed this talk, but he decided to change a little bit because he will do it in different steps, because he wanted to connect with the general seminar on transitions that we started last week. And I think it's actually a great idea to do that. And so as far as I can understand, he will start to talk from a very theoretical way of what is complexity. And so to say, for people that knows a little bit about the theory of complexity, you have what we could call stochastic complexity, which is randomness, random complexity, or some people in mathematics call it like infinite complexity, so the fact that you can't make it something deterministic. And you have also an interesting concept that was born from the theories of chaos that are part of the theory of complexity, that is called strange attractors. Strange attractors is the fact that complexity becomes deterministic. And so I think his talk will be some kind of an oscillation between deterministic complexity and random complexity from one to the other, and how it will allow to transit, to go from one cycle to another. So it's exactly in the theme of the Institute for Advanced Studies, because it's basically about transition. So how we go from one equilibrium to another one that will constitute some kind of cycles. And what is interesting is that now we are going to enter into also the discipline, because at first, as I said, it will be very theoretical in general from like the theory of complexity, but step by step, he would enter into his specialty, like economy, econometry, and also finance and financial cycles with different models that will take into account this complexity, I will say, in a way, paradox. So thank you. We are very glad to have you here, and we are going to listen to you very carefully. And please, don't be too long. So, I mean, don't be like me. Because it would be great if we could have some kind of a discussion all together to make something happening, like the energy, as we said. Thank you to be here.
Thank you very much for this presentation. And yes, the initial idea was to explain financial crisis, Black Swan events, but then I wanted to connect to the talk that Raphael gave. And also, I wanted to explain the basic concept, because otherwise we cannot understand each other. And that is important. How can I move this thing? Do you have an idea? With the computer, so it's manual. Okay, good. Ah.
Stochastic, random.
Thank you very much. Okay, good. So this is the outline. I prepared 141 slides. So, and then as Raphael mentioned, it's not possible to explain everything. So we will go step by step, and maybe we'll divide this in 2, 3 sessions. Like you said, you have this book, fantastic book, in which you want every Monday to explain something, part of this transition. So it could be an idea. Okay, so let's start from the outline. So here you see many topics, but as we said, we start with some definitions, and then explain then with this model, with this sand pile, a simple example of complexity. And then, well, then I will show you a strange attractor, and why it's called strange attractor, because it's a kind of geometrical figure in which you can see that the trajectory of the dynamical system stay inside. And then I will show you some definitions regarding what we know, but also what we don't know, and what we don't know that we don't know. There are things that in finance, economics, and so on, but also in practical life, because to make some decisions are very important. And then I will go through random versus deterministic complexity and business cycles. What business cycles are? Well, essentially, we know that the economy sometimes is going well, sometimes not. And also, we may have very deep recession. And this is something that we don't want, or at least we want to anticipate. So the reason why I'm studying this is to understand whether there is something deterministic, in the sense there are some laws that allow us to understand what is going on and to predict, to prevent this phenomenon. That's why there is a model, economic model, which is purely deterministic, but behaves stochastically. So what I mean stochastically, that is random, at least apparently. But in reality, there are some equations, deterministic equations, that drive the system. And by deterministic, I mean, well, we have mathematicians and we know that they understand everything, but essentially, for example, a straight line is something deterministic. I know the x. If I know the x, I know the y as well. But then random, it means something like this, that, for example, dice. When we have 1, 2, 6, no? And then what is the probability that we get one of these numbers? Well, the probability is 1/6. But then do we know in advance which number we'll get? Of course not. So stochastic, we don't know what is going on in the future. Deterministic, but we know that some models that are deterministic may behave in a stochastic way. So unless we know the initial condition, we will never know what is the next occurrence. And one simple example is about weather. We know the law of physics, but we don't know exactly the initial condition. So for this reason, we cannot forecast exactly what is going to happen in 1 day, in 10 days, in a month, and so on. And there is a Sad then will explain you how forecasts are made. There was a nice talk between two people, and then he will show you exactly this example, how we can make forecasts. Where it was that? Between India and the USA? Okay, so advanced science. He will explain you this. This thing, okay. Well, then, as we said, let's start from the simple definition. And the simple definition says that at the end, this definition is something challenging. So many cannot even say what a complex system is. And then even someone says that, well, we don't need to define it because whatever we say is meaningless. But then we deal with complexity. We have complexity in life. And then what a complex system is. Someone says that an airplane is a complex system. Someone argued that it actually is not a complex system, but is complicated. So if we cannot define what complex system is, at least we can explain some features, can identify some features, and based on those features, we can say what a complex system is. So one possible explanation is that we have many interacting components, or agents, economical agents, for example. And then there are emerging properties like we have in those agents, those components, but all together they behave in a very different way from the behavior of the single component. And then there is no central control. The system is self-organized. And then also there is no linear feedback mechanism. So linear, this is linear, and like this, you know, 3x plus 2, for example, just an example. But then this thing, so let me square it, sorry. Then maybe it's not linear, okay? Just to explain what I mean. So non-linearity, it means that, well, there is no proportionality, direct proportionality. And then, okay. Some definitions. So one definition is what we already said, non-linearity. Another definition is that, again, what we said, that we have a large number of agents. And then with the self-organization, and there is no central control. And then the last one is what we said before. So the last characteristic that altogether they behave differently. Okay. And here we have philosophers that, like Raphael, they try to debate because they argue, because they like to do it, because they cannot they cannot agree on anything, so they need to argue.
That's it. It's a disease.
Okay. So that's why we have space and for this definition, for arguing in the where is it? The Kathmandu, where you went last time. Okay. So you can go there again, explain these things. You can take the chance. Okay, so there are some properties. Then we have structurally complex systems that are like a clock, or other systems that are simple. But the clock, we know that behaves in a simple way. Instead, the weather is behaving in a very unpredictable way. So the structure is relevant, but also, again, the interaction. And there are other examples like the brain or internet. Let's move forward. And then here there is subjectivity in this kind of framework. So there are some complexity also depends on the perspective or the context that we take. And then let's make a simple example regarding finance, financial markets. So how, if there is a 1% change in the price of a share, let's say a drop, is this dramatic? Is not. Minus 10%. So that very much depends on the risk, what is called risk aversion people. If people are risk averse, more risk averse, they will worry very much. If people are not so much risk averse, they will worry less. And then we have people that altogether they react in a different way. But as we said, the sum is not the result of the complex behavior, but the complex behavior is the result of the interaction. So the interaction is the key. And then, well, then there are two ways approach or way of seeing complexity. And then, well, you know, when we interact as human, we also are part of this change. So maybe we can not only be the subject, but also the active part in this interaction. Then, again, well, in the past, it was much more difficult to study complexity, but thanks to modern tools and like surrogates, computer simulation, and so on, we can try to model complexity in several ways. And then we can manipulate. So we can do experiments, because in physics, to make an experiment is easy. We can, by definition, in order to prove something, you must reproduce it. But in economics, it's very difficult, because you cannot go back into history and to check what would have happened in a different context. But thanks to simulations, thanks to model, we can at least have some understanding about this. Okay. And then why we need this kind of science? Well, because it's everywhere. This kind of complexity is everywhere. It is in physics, in biology, in society, and so on. And this is a kind of approach that we need, in the sense that we need a holistic view in order to understand, well, the life and the world in which we are living. And here there is some example. So we said that a lot depends on relationship, interaction. So we have three kind of state. One is physical, the other one is biological, and the other one is social. And then we have here different kind of systems. So a random system, when is a physical system, could be a gas. A biological system, when is random, it could be a pond, the life in a pond. And then when it's social, we have crowds. And so I will not go into detail, because then we said that I must speed up. But at least I would like to show this snowflake. It's a nice picture. So at least pictures, we can comment pictures, we can. And then, well, this is an example in which there is a coordination between the different elements. So large-scale behaviors, we said, plus self-organization. And then let's have a look at this, this example. So let's start with this sand pile theory versus domino. So in the past, there was a theory that, was saying that if one country falls to communism, then communism will spread everywhere, sorry. Then the world will be ruled by communists. And we don't want that. That's why Vietnam. So it was very important to win that war. And now in Ukraine, no. If Russia wins in Ukraine, then they will march up to Lisbon. So that is the idea, this domino. Instead, there is another one, that model that is called some pile theory, in which we show that maybe things are not so linear. And then let's have a, sorry. Let's see what can be described with this very, very simple model. Sorry. Is this working? Okay. This could be a model, again, that we can use also for analyzing politics. And then, well, it's called, in this way, Abelian, from Disabel, that is a mathematician. And then is able to explain complexity in a simple way. Is a self-organized criticality, in the sense that there will be an event, like the example that Raphael made last time, that will change completely the system. So like we have in the past, he mentioned the drop, no? The water drop, no? Drop. The last drop will change completely the situation.
Exactly, self-organized critic.
That's why I took this example to connect with what you said. And then this mechanism may change again the situation. So you have a drop in a glass. In this case, you have some grains of sand. So for a time, you will not see any change. But then suddenly, with just one grain of sand, there will be a sudden change that will completely change the situation, the system. So, and then there is also another game that is called game of life. So is either 1 or 0. I don't know if the mathematicians here, do you know it? Yes? Do you play? And then there are simple rules. No, one is alive, the other one is dead. And then the rules are like if there is a cell or energy, you can call it the way you like. And then there are, next to this cell, there are 2 or 3 active cells. Then this cell will be alive, otherwise will die. And then what this simple example explains things like, for example, a glider that is a moving structure, an oscillator. So like oscillator, a pendulum, for example, no? Something that goes after some time back to the initial stage, or still life, so a stable structure, something that is stays. And this thing is, well, is a Turing complete. And is sensitive to initial condition. Let me show. And now we have a video because it's nicer.
This is John Conway's game of life. There are points in space, sometimes referred to as black is on, white is off. And you can also call it alive or dead. Now there's a simple rule that tells us whether or not cells stay alive or they die. And that's this. If a cell has it has no neighbors that are alive, it dies. If it has just one neighbor that's alive, It'll die, so both of these will die. But if it has two neighbors that are alive, it'll stay alive. So look what happens to this cell. It's going to stay alive on the next moment of time. Or something else weird happened there, right? These two died, and these two became alive. They were born. Let's look at that again. This cell only has one live neighbor. It's going to die. Same here. It's going to die. So on the next generation, that one will die, and that one will die. But there's a rule for birth. And the rule for birth is this. If a cell has exactly 3 live neighbors, it will be born. This cell has exactly 3 live neighbors. And so does that one. So these two will die, and that will be born. And you can see what's going to happen now. By symmetry, it's just going to go back to a horizontal bar, and we have now just an oscillator. We're continuing here with Conway's game of life, and let's look at this pattern. We've got a square, we've got a square, we've got a square. Those are all on. These pointer cells are on or alive. They're energized. So, this cell has 2 live neighbors. It's going to stay alive. This cell has 2 live neighbors. It'll stay alive. This cell, same 2 live neighbors. It'll stay alive. And let's look at this one. That one has 3 live neighbors, so it's going to be born. And that's what happens. It's born. Now, this is a stable pattern, right? Each of these cells has 3 live neighbors. It's alive, and so it's going to stay alive. The surrounding cells don't have enough energy. They don't have enough life around them to be born. So this is just going to be a stable pattern and actually stepping through time, but nothing happens. So that's an interesting pattern. Let's look at this pattern now. Hard to say what this one's going to do. But look what's going to happen. We need to use computers to figure this out. If you had to calculate this by hand, that would be a little rough. It's going to change. Now you can see it looks like it's rotated itself, right, horizontally or vertically. And the same again, you see a reappearance of a pattern. And look at that. That's just back to where it was, except it's back to the same pattern that it was, except it's shifted one to the right and one down. That's a glider. It glides. It moves.
Okay. So, as I said, game of life, very simple rules. We have moving structures, oscillators, and still life, so stable structures. And again, is Turing complete. So, but what is the issue? This thing is sensitive to initial conditions. So if you change the condition, you will get different results. Okay. And then instead, this abelian sand pile is different in the sense that you will see that it is independent from that. And then you have multiple cells that may be at the same time unstable or stable. And then there could be a tuple in the sense that there will be a change in the structure of the system in any order. But at the end, you will get this stable configuration. And because it's commutative in the sense that is independent from the order, then it's called abelian. So let's make an example. We have 2 cells. We said that 4 means that there will be a tuple. So they will spread this sand. And this is a possible configuration. We had 4 and 4, 8, and here again we have 8. So the sand changed position, and then here we will have a next step, because this thing, we said that we cannot have more than 3 in each cell, so this will change, and this could be a stable configuration. And this is possible asymmetrical pattern. But what can happen if we have more cells? So this way, you see, the progress could be this one, from 0, 4, 4, 4, 4 to 0, 5, 5, and then to this one, which is stable. But then we will have also further toppling. And this is when we have million grains. And then this is self-organizing. No one is moving one grain of sand from one place to another. The equilibrium is an equilibrium that is achieved by itself according to the rules that we stated. And you see there are different patterns. I'll show you on enlargement. This is the center. And this is the edge. You see this kind of triangular islands. So what is, well, someone has studied this thing and then has found that there is a critical threshold. So on average, this is the number of grain of sand that should be in per dot. If it's more, you go from a stable condition that we said that the drop after drop, nothing change. But if you trigger this level, then you will have sudden change in the system. Yes?
The 2.1 corresponds to the fertility rate for a nation.
Yeah, and then is the fractal.
Any relation or
No, that is the fractal dimension. But yeah, this is nice to study this thing. How do you get this thing, this number? But because what is nice that again this system is very, very simple. You have a couple of rules. You can simulate in a way you like, and then you will get exactly this kind of. And this is deterministic. It's not stochastic.
That's interesting. You say that it's very simple but complex.
Exactly.
But it could be complicated and not complex.
Exactly. 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 That's why I wanted.
I like it.
Okay. Well, another thing. For example, we have achieved a higher level, 3 grains per spot, but then this thing is unstable. There is something that is called unstable equilibrium. So when we have an equilibrium, then but it's sufficient one drop, one grain of sand that will change everything. So and then this is the stable configuration. And then we have something that is called power law. And then, well, this is very common in different fields, from natural disasters to city population, internet traffic, and so on. And then essentially you have that when you have big disasters, the probability, the frequency is lower, and the opposite. And this is the expression. And then there is this kind of Pareto principle, is rule of thumb, that says that the majority effects are from the minority of causes. And And then let me show a strange attractor. Well, everyone has seen this kind of beautiful thing. This is called butterfly, Lorentz attractor, and so on. What is the idea here? That, well, when there is a structure like this, then the dynamics stays in this kind of area. And then I show you just quickly an example. You see, this is the trajectory, and then this is in a different dimension, 3-dimension, and then you see the way in which we can change the coordinates, and then we have different views of this strange attractor. Okay. So again. These are the equations, but I will not go into them because Saad told me not to do that. And then, well, there are broader implications. Well, these phase transitions. You wanted to talk about transition, and this is a physical example, very simple example, but again, complex, not complicated, simple and complex. And then we have critical states, avalanches, and self-organization. And then, well, these questions are for you that you are philosopher. You can predict those avalanches for sure.
Many things to say.
Yes. And then, well, later in this presentation, but not today, I will show you an economic model, how to do these kind of things, but not today. Well, and then there are some connection in mathematics, like tropical geometry. And, well, another thing is this spanning tree. And I just mentioned the names because we don't want to discuss these things. And, well, and then this model show the complexity emerge from simplicity is what he said, and then demonstrates self-organization. And then, if you allow me, I want to introduce this section, and then I will stop after this session. So there are things like this table, like there are things that we know that we know. There are things that we know that are unknown. And there are things that are unknown knowns, but also there are things that we don't know at all that we don't know. And then, well, there is this example regarding knowns that we are aware, things that we are aware, we understand. So physics, for example, the law of physics are known. And we have data, we have models, and so we can explain everything. So the gravity, for example, we can explain that. And then also there are things that are known that are not known. So for example, the financial crisis. We had financial crisis in the past. We know that a financial crisis can happen. And then this is something that, again, can happen. So we know in advance that something like this is expected. And, well, this is an example of unknown knowns. So you see, this is the volatility. What is the volatility? Volatility is the risk, the standard deviation, but also the risk. And you see, for a long time, the volatility was small, and then this happened. This happened between 2007 and 2008. And then, well, if that is the risk, you can imagine what happened to the portfolio, to the return of the investors. And here, there is an example that I made to SAD. This bank, real example, this is based on real data. So there was a model. This model of the bank A was expecting 5 exceptions to the risk. What is this exception? So each bank measured what could be the risk for next day or for next month, whatever, and then expect some exception. And this is a probabilistic thing. So like here, we have 1/6 probability of 1. This is probabilistic thing. So what is the probability of that? 1/6. What is the probability of having an exception of a loss? And this exception is a loss over a certain trigger. Well, the probability was 5. So 5 times could be in a year that there would be a loss higher than a certain level. In 2006, this was fine because 5, 6. The same, another bank had another model, 4 expected exception, 5 real exception. So there was a loss in 6 cases and 5 cases here. But here in 2007, the first quarter, 3 exceptions. The second quarter, 4 exceptions. The third quarter, 7 exceptions. So, and the last quarter, 10 exceptions. So this was a huge failure. Unknown, unknown. Things that we don't know, that we don't know.
The average for bank A in 2007 is
No, no, not average. You have to do the sum. Sad, please explain. I want to know how many times I lose, not on average. And the sum of all my losses is the sum of this. Yes. So this is a real thing. This is not estimated, this is not a model, whatever. It's based on real data. And then, well, there is epistemology of unknown, unknown that you like this example because then is...
But I don't like that research.
Because maybe someone can say, well, I can make a statement and then prove me that I'm wrong. But if the proof is very difficult, then, well, yeah. Then, for example, there is a teapot. No, there is a teapot between the Earth and Mars. And then this teapot is so small that you cannot see it. You can see with the telescopes. So prove me that I'm wrong. And so this is a kind of epistemology, something that is important to understand in order to avoid some logical mistakes.
I will discuss that because I don't agree with that argument.
I know that you like to disagree because that is your job.
Because it's an argument that I think is not a good argument.
But I like philosophy because is a way to challenge things. And then I will stop with this definition of Black Swan, because otherwise it would be too much. You have some events that have these 3 traits. So unpredictable, they have a massive impact, and they can be afterwards, they can be rationalized. And then where this comes from. So in the past, black swans were never observed. So for anyone, a black swan was something impossible. Swans could be only white. But then, sorry?
In the previous slide, so from the definition, so black swan can be something positive, because we always imagine the black swan it's a negative thing, but from the definition it can be something very positive.
Something that has these three characteristics. Massive impact, of course. Could be something that changes your life. For example, beautiful, I don't know, wife, whatever. You will change completely your life, and then, well, that would be, what is it, the gift of God, no? And then, well, so something that was impossible, but then, after the discovery, represented a logical fallacy. Why we should suppose that at all swan should be white, could be any color. It's just a matter of evolution. And so afterwards, you can rationalize this this feature. And then, insight, the unknown are the most challenging, the most relevant thing that may change completely the way in which we perceive things. So I think that I will stop here, otherwise we'll take too much time. So if you have questions and aspirations, desires, as Raphael said, I'm happy to answer.
I have plenty. You are too mesmerized.
Yes.
So for me, if I can say, I think there are many things very rich, because in fact it's very broad in a way. You have, I mean, described many things about complexity theories, not only theory. So for me, I will not ask specific question, but I would think that what could be discussed, and we can discuss it extensively, but maybe we will not have time. It's a long run thing. Is first the very nature of what is a rule, because there's an idea, for instance, when you're with the game of life, there are rules that define a certain kind of thing. So what is the nature of the rule? What is, you know, I think it's kind of tricky. The second thing is that I think would be interesting to discuss. It's the, again, question of nature. I'm sorry, because I'm a philosopher, so I'm always into these kind of things. It's what is an initial condition? Because I think when we are thinking about initial conditions, it's like if we were thinking initial conditions as a finite number of conditions. And the real problem is that the conditions are never finite in the real world. So when we are thinking initial conditions, it's like if we were in an abstract world. That's the reason why, in my opinion, but it has to be discussed, we are always able to predict what is happening in general, but not in detail. Because if we enter into the detail, it almost never works. Like the more you go to the smallest event, the less. It's like you were talking about broadcast, weather broadcast. That's exactly that. You can predict in general, but if you go into detail, you say, let's say about a plane that is going there. We know it knows that there will be something that will happen. In fact, it will not happen exactly there. Why? Because the number of initial conditions are infinite, but in order to calculate, you need to make it finite. So, in my way, even the very idea of initial condition is to reassure us, but in fact, it doesn't exist in itself, initial condition. So it's one of the points I wanted to make is I think it's a little deficiency in the theory. One of my critiques that I was talking about when I was talking about the deficiency of the theory of complexity, it is specifically that. Specifically when we enter into deterministic complexity. So all these kind of, but just to discuss, and it's we will have time to talk about it on the long run on your.
Well, regarding the initial condition, well, we know that in physics we have some laws. And then, well, if those are deterministic, but what we said, that the problem is the interaction. And also, well, to know exactly the initial condition of a system in general is very, very difficult. Not only because of what you said, but also because when you go in quantum mechanics, for example, then you have something that is indeterminacy. And that's why Niels Bohr was saying it's difficult to make predictions, especially about the future. I don't know if it's clear this. So it's difficult to make predictions, especially about the future. So it was a funny way to say that exactly. So to predict something is extremely difficult, and then, well, we know that we may, with some models, what we said, toy models, simulations, whatever, we can reproduce something, but for sure, we will never achieve the detail or the precision that someone is dreaming of.
But you
So,
know what's
and but
it's exactly what you said.
Yeah.
You said when you were saying that you rationalize, but a posteriori. So you say, oh yes, that was determined, but like as Bergson would put it, but you need to turn and to go backwards, and you say, oh yeah, backwards. When you look backwards, say it is all that. But except that you can't say it for the future. So
yes,
the paradox is that you can't predict the future as long as it is calculated through the past, which is some kind of a paradox, because it's always a posteriori. So it's not of any use in a way.
yeah. Sometimes also you can see this in movies. So you start from a situation, and in order to understand where you are in this situation, you must go backward.
That's it.
And then maybe you understand what is happening at the moment, because then you have a better understanding of the past. So that's why we need to, let's say, be holistic in the sense that we need some philosophy, some mathematics, and so on, in order to understand what happened in the past, in order to get to this point.
So it's not only in terms of time, but also in terms of scale. So you said that things in general can be easier to analyze than when you go in detail. In physics, there is a different example. When you go big scale, you have relativity, you describe things very well. When you go small, you have quantum mechanics, and you can describe things very well. But between the two, it's the most difficult thing, which is the complexity thing, because you have many atoms and things like that. You will have other sciences, material science or mechanics, things like that. So you have it is based on quantum mechanics, but when you have many things, it becomes difficult. So sometimes the detailed thing is easy. The big thing is easy, but between them it's hard.
Yeah, I don't agree with what you just said, to say the truth, because when you're saying when you look at little things like in quantum mechanics, again, you can describe, but the definition of what is to describe has changed in the meantime. Because what is to describe in regular physics is to describe actually law of physics, causal law. That's the reason why Einstein didn't agree with the fact that quantum physics was a description. For him, it wasn't an accurate description. And he was saying, and so the closer to the smaller we get, we can see, oh yes, now we have a description according to what is quantum physics, which is not a description according to what is regular physics, because it's acausal, it's undeterministic. So it's not anymore a description in a regular sense. You know what I mean? So it becomes something like exactly what I said when I said general, because you don't know when the collapse of the wave function will actually happen. But just probabilistically.
Yeah, probabilistically, but maybe this is the way to look at work. Probabilistically, this is what quantum mechanics says. So
I know.
It changed the rules. But
Exactly. So it changed the very definition of what is a description.
Exactly, yeah. But it gives
So
equations. It gives equations that explain things in terms of density function. So in terms of probabilistic way, but it's at least a description which is accurate. But when you are between the two, between the big and the small, at least in physics, it's when it becomes hard.
Usually that's why we need mathematicians, we need philosophy.
Yeah, but I mean, even in mathematics, there are some rules that we don't control when we get into big numbers. But I mean, it's just we have this big discussion with Gregory Shaitin when actually we were talking about a different kind of infinity, as you know, and at one moment we're just lost in translation from those different kind of behavior, even for something that are abstract, like the behavior of abstract things. But there is something that I wanted also to ask, is because when we are like the thing with the rules, it's just like we decide that there will be some properties with numbers. For instance, it's alive when there are 2, and it will be born when there are 3, etc., etc., etc. And you say the important thing is the interaction. True. But when we say it's a property and we define this property with a certain number, what you said, we don't say what I called the other day, I don't know if you remember, so we connect with my daughter, the glue itself, not in terms of number. What is the nature of the interaction? Because an interaction is not a number, a real interaction. An interaction is the fact that there is a link, but we don't know the nature of the link. It's a little bit like Newton, because Newton, he had the idea of the theory of gravitation. He put it into mathematical expression, pure mathematical expression, but himself said that he doesn't know what is the nature of the interaction between the moon, for instance, and the Earth. He just sees that mathematically, it is mathematically there is a relation between the mass, and the distance. But at the end of the day, he said there might be something between, but he doesn't know what it is. That's the reason why he said that's the will of God. So even now, I think we haven't solved the question of what I call the glue. So what is the nature of this interaction? What is the nature of the interaction itself? And that's why we feel obliged, or we feel that to invent properties with numbers, saying this little cube is, if there are 2, if this is happen, yes. But in real life, it's not numbers, it's the interaction itself.
Well, that's why in these examples that I made, the interaction is what is around. So this thing, no? If if all around is white, the interaction is that this thing will disappear.
Yeah.
So in this simple example, toy example, we have seen that this creates a different kind of status, from stable to, I would say, transitioning and so on. But at the end of the day, of course, then when we want to model the society, when we want to model the weather and so on, this kind of interaction is something that makes things very, very much complex and unpredictable.
But if we don't even talk about a complexity, we know there is an interaction.
Yes.
But we are like inventing the properties, saying there is this rule, there are those rules, and those rules determine a certain kind of behavior, different kind of property. You have shown it brilliantly and perfectly. But it's like when for instance, it's like when we talk about the collapse of the wave function we just talked about, that makes the world with different things happen. Like before, it's just a friction, as some physicists will say, it's a friction of the void. Yeah, but we don't know what that even means. And so what I mean is, the relation, like the concrete relation between the object that you have actually formalized, we don't really know what it is. What is it? It's just because there is a formulation. So you put it into a formula, and you try with this formula to imitate some kind of behavior that we find in nature. And so mathematically you say, okay, this is the kind of behaviors that you can find in nature. But in nature, it's, as you say, the interaction is, even etymologically, what is between those two? So what is the nature? What is the nature of the thing? That's the point that we haven't solved yet in science.
Well, in the macro level, you know that there are some kind of laws. And then from those laws, you know more or less what is going on
I
to
know,
happen.
it's not only a question of predictability.
No. I'm now talking about how people behave together. Sorry.
An example, for example, in physics, there are laws. We didn't invent them. We
Just discovered.
no, we saw in real life, and we saw that some laws apply to the phenomena that happen, and we can predict weather to a certain extent. We can predict weather.
Yes.
We can predict the behavior of structural components. So we can do that because we have the tools, and we have also the laws that bound the interaction between the system. So, for example, in mechanics, we always want to minimize a certain energy. Or, for example, sometimes we want to maximize the dissipation.
Oh, yeah, I know.
So, why these laws apply to what we saw in real life?
It's not the why, the question I asked. Actually, I was. It's not the why.
But
For me, it's not the why.
Yeah, but we can go further. It's what is energy? We don't have we don't have a definition.
The dynamic, etc. But
no, I can define it from a mathematical point of view, but the energy, the deformation energy, for example, the plastic energy. What is energy? So maybe I think there is no definite answer to this.
No, I'm not saying there is a definite answer, but I think maybe there is in the way we perceive the world. I'm sorry, I'm a philosopher, so it's what comes to my mind when I say the very idea of defining. Suppose that we need to have a certain number, for instance, of parameters, and just the fact that we want a certain number of parameters, right away, it doesn't fit into what is the real world. No, because even when you say law, even the very notion of what is the law, I think now we will. It's even a little bit more accurate to talk about force, because you talk about dynamic when we talk about
yes, but we can predict a lot of things. It's not.
Of course we can. It's what I'm saying.
Without knowing, for example, without knowing the
yeah, exactly.
to the atomic level, the detail.
I know, but there are two. You know, there are three ways in science to assert the truth. No other doesn't exist. No other way. The first one is what is called pragmatism. So you know it's true because that works, but you don't really know why. But you try to have some ideas why, because you know it works. Like for instance, medicine has worked mostly like that until the end of the 20th century. Now it's a little bit changing. The second is what is called factualism. It means, oh, you have made the experience of it. So for instance, I met you, and I said, I know you because I've seen you. But when I'm saying I know you, what do I know? I mean, I know what I've seen, but I don't know your DNA, for instance. Yeah. So it has also its limit. And the third way is what is called coherentism. Actually, it doesn't happen. Doesn't have any reason, but it is so coherent that it has to happen. I forgot something. It's like it has to happen. So when we say we know, usually from when science started to be mathematized, the idea was to limit pragmatism, to limit to even factualism, to make it all coherent. It's what is a law. To say, oh, it's all coherent. But doing that, we try to limit even the scope of what is the real world because it was too complex. And this time, not complex, but because it was too complicated. And so make it more simple, it becomes more coherent. But in becoming more coherent, we could build machines, things that work, etc. But in a way, we lost track of what it really is. And I think now science is coming back to try to understand what it really is. And the question of transition is exactly that. Because we don't know what it really is, because we don't know when it will happen. There is this thing about what you call critical, like the last thing. We say, oh, it's partly causal, but when we apply another model, it's not causal anymore, etc., etc. And so I think it's like if we have been so much into the mathematization that we forgot about the very substance of the real world, what I call the glue, like the glue. I don't know if I'm clear, I just try to...
Yes, but...
We need, I think
if
that...
I follow the glue, I will never...
If you follow the glue, you can't do physics anymore. Just an example in history of physics. Just an example. When you want to calculate what is a motion in physics, it's weird. Because when you want to calculate what is a motion, you just do it with immobile things to say at this time, at time t1 it's here, at time t2 is there, at time t3 is there. Except that it's never at time t2 there because it's in motion. But the only way you have to calculate what is a motion is to add the opposite of a motion, which is something that is. And so there is some kind of something tricky in doing that. I understand. You can't make any calculation if you don't do that. So I understand it. But still, if we found some paradox doing that and some limit in our calculation, it might be because what we think is the picture of the real world is just something that makes calculation easy, but it's not the real world. It's just what I want to do. But of course we need to calculate. So, I mean, I want machines. Anyway, I'm sorry.
Can I just say something? Well, thank you for your submission. And I've been thinking, I'm a medical doctor by training. And from what Raphael just said, it's like medicine has gone ahead of you people who just arm and think. Because medicine in Morocco is the same medicine in America, is the same medicine in Ghana.
Mm-hmm.
Because medicine has been able to go beyond all these speculations. The science is now more real. If you have malaria, give you medicine, you will recover, you will see it. You don't speculate. But economists, weather forecasters, and now philosophers, you propound theories, and we never agree. Why is it? Is it because you are yet to improve on your models? I like the models of the physics because physics model, gravity is a little more exact than the models of economics. So what is happening? Are you behind, or are you not making progress, or is it just the nature of your job?
Well, the thing is that in medicine, for example, in order to discover a new drug, you need to prove that it works. And how to prove that it works? You need statistical models. So at the end, what you see is the drug, but what is behind that? What was required in order to develop that drug maybe is something that you didn't see. So these kind of models is the combination of some molecules, good or bad, is something that you didn't see, but is there. So this kind of science is the basis of the drug that you give to your patients. So I know that for you it's easier because you see the reaction.
Yes.
But before to give to produce on large scale this drug, you need to do years of tests and so on. And again, there are models in order to understand if the combination of some molecules are good or not. And then you have tests, you have field experiments, and so on and so forth. So, and these are also based, everything is based on models and statistics. So it's not behind, but it is something that beside what you see.
And it's the difference between a model and a theory. Sometimes people, they pretend that theories are like models, and there are many, maybe not you, but economists that talk about models when I see them, and talk about theories, but in fact it's just models. It's very different models, because models, it's actually when you are able, it's just you are able to predict statistically what is going to happen, etc., etc. But a theory is explanatory, not only of what is happening, but in a way with some hypothesis why it's happening beyond the thing itself. That is a theory, and a theory is made of concept. It's not made of different reactions that you could predict.
So exactly, and this is something that I cannot explain, is the theory at the base of the model. And then, well, in economics, you will see something that is expressed in scientific terms, in objective terms, but actually is really ideological. It's kind of to be part of a religion, a dogma. So, especially with neoliberalism and so on. So that is a dogma, and if you don't follow this kind of ideas, not these ones, the ideas that are called mainstream, then it's a problem, because then you will not get funds, you will not publish your articles, and so on. So, in a way, you have mathematical models that pretend to be objective, but in reality, there is a lot of ideology. Right. And then religion, dogmatic religion, is something that we have nowadays in economics.
The initial mental condition.
Yes, yes.
You believe in God.
Sorry?
I think mathematicians now believe in God.
Some mathematicians.
Well, the one thing that is what
can't talk to believe in God.
You may believe or not, but one thing is important, that there was in the past, there was a program that failed, because there was a mathematician, for example, that wanted to say, well, we have a systematic, consistent, coherent theory. And then someone like Gödel said, well, it's not possible. So you have a proof that even in a given system that is axiomatic and so on, well, you will never have this kind of 100% consistency, whatever. And then, well, if you believe in God, that means that there is something that you cannot achieve, that is perfection.
So
the unknown unknown when you're an atheist.
Yes.
The known unknown when you're a believer.
Yeah. And that's why you say here, you say inshallah, because yes,
yeah, sure.
if
yes.
God will.
If God wills.
Yes, exactly.
Inshallah is interesting.
Yeah. Because then you have the limitation, you have the understanding of a limitation of your action, of your rationality, and so on.
I like it. It makes
You are
makes you more humble.
Yes, exactly. That is the thing.
Arrogance. Some scientists are very arrogant. They believe.
Well, some yes, some no.
It's more arrogant than other kind of belief, because it's the belief that it's not a belief, which is even like the belief square.
So, questions or desires?
If there is a question, that's fine. I could see that.
But Saad has to explain how the forecasts are made in, well, in the US and India, you said. Please, we want to listen this example.
You have the floor. The floor is yours.
No,
winter was coming, and it this guy in the public television who's in charge of the forecast, and he doesn't know what's going to happen. So he calls the Indian, the chief of Indian reservation, and he asks him, "Do you know if the winter will be cold?" And he said, "Yes." So he goes back on TV and he said, "The winter will be cold." And then people tell him, "Is it going to be cold or really cold?" So he calls the Indian guy and says, "I think it's going to be really cold." Then he goes back on TV and he keeps going. And then one day he asked the Indian guy, he says, "How do you know what the weather will be like?" He said, "I'm looking at your forecasting program on the television."
So this is an example of interaction.
For sure. And it's an example of systemic causality. But not complex, very simple.
Yeah, exactly. Okay, so I think that for now it's enough. And then maybe we make a
It's a very
second.
good introduction to
Yes.
our further discussions,
Yes.
I think. So thank you very much.
You're welcome.
And thanks again. So now please take advantage of this wonderful buffet.
And just for especially for you two, if you can tell your colleagues that we have this kind of event, and of course if you want,
They know.
yeah, but
They
too
do
bad
know,
for
yes.
them. But if they want to
They are
follow
not in the,
on
they
this
know,
discussion,
they know.
Giuseppe is Village 61, Village des Chercheurs, so you can come anytime and discussion with him on these topics for
And as you can see, it's very alive and very discussion is very alive.
free of charge.
Free of charge too.
That's nice.
Free of charge also in the different meaning. Also the meaning that it's not